So is there any way to make iterative method converge faster on a finite grid? So there has been a very effective way to do this. That is called multigrid. Okay. So the idea of multigrid is to actually take advantage of the fact that the Jacobi and Gauss-Seidel-like iterations, they converge very fast on a coarse grid. Okay, and the effect of the iterations is essentially smoothing out the solution. I mean, and not smoothing out the solution, but smoothing out the solution error, as we have just seen. The solution error initially is basically just the true solution itself, but over time the solution error gets smoother and smoother, right? So let's actually look at this again. X equal to, initially we perform one iteration, right? And if we look at the solution error, which is the true solution minus x, is essentially the same as the original picture, right? Maybe a little bit different. And then if you perform a few iterations, let's say we perform 10 iterations, and let's make another figure and show the solution error again. So figure 2 is the new solution error. So what is it compared to this? It's a smoothed version of the original solution error, right? So basically the idea is when you apply the Jacobi iteration again and again, the error becomes smoother and smoother. And if the error becomes smoother and smoother, you can actually represent it better and better on a coarser grid. So the idea is, what if you start with a fine grid? Okay. What you start from a fine grid? Okay. You iterate. Okay. The result is the solution is going to be smoother, right? So basically, you interpolate the solution, which is now smoother, to a coarser grid. Okay, so now you iterate on the coarser grid. Which actually makes the whole thing converge faster. All right. And particularly if you imagine if we ended up with a 3x3 grid, the Jacobi iteration actually converges in one step. Because for a 3x3 grid, the size of the matrix is 1 by 1, right? By moving the diagonal component to the left-hand side, I mean the whole matrix, a 1 by 1 matrix is the diagonal component. So a 1 by 1 matrix should converge with one iteration on Jacobi method. So the smaller the matrix is, the faster the convergence is. So basically, if we are going to be able to iterate a few steps and get a smoother solution that enables us to interpolate to a coarser grid, we can iterate on the coarser grid. And then we interpolate back to finer grid. All right. And then we keep iterating again. So that's the idea of multigrid. Okay. But there is actually a lot of a bit of tricky thing over this. So here, the key question is, what do we interpolate? X? Pardon? The solution I have after a few iterations? But that's problematic. Because the solution, is it guaranteed to be smooth? No, actually, the kind of solution we wanted to get at the end, like the picture we showed you in the beginning, is actually not smooth at all. So the solution actually is not guaranteed to be smooth. But what is going to be smooth after a few iterations? the error, right? The solution error. The solution error is going to be smooth. But do we know the solution error? We don't, because if you want the solution error, you actually need to know the true solution. And if we have the true solution, we don't have to do this at all. So here's a dilemma. Like, what do we actually interpolate to take advantage of the fact that the solution error is smooth? Well, we actually do the next best thing to actually interpolate the solution error. We interpolate the Laplacian operator, or the matrix operated on the solution error. Okay, what is the matrix operated on the solution error? Let's take a look. So we are solving AX equal to B, right? Okay, so currently we have an xk, and the solution error ek is xk minus x. So what is A times ek is actually A times xk minus A times x. So although we don't know what the true solution is, we know perfectly what A times x is. That's my B, right? So this is A times E would be actually A times xk, which we already would be evaluating during the iteration process, minus B. This guy is defined as the residual. The residual is basically how the current xk is not satisfying the solution, right? So if the residual is equal to 0, that means A times xk is already equal to B, and I have already solved the equation. I mean, in some sense, the whole point of iterative method is to drive the residual from something that is very far away from 0 to 0. Okay, so what we actually ended up interpolating in multigrid is actually the residual. So why is it useful in interpolating the residual? It's because on the cost grid, we no longer solve the original equation. We solve the error equation instead. We solve this A times EK equal to RK. I mean, if we know what is EK, then we would know the true solution, right? We just add, we just subtract the error from the last iteration solution, right? So then we would get the true solution. But of course, even on the cost grid, we can't solve the equation exactly. So we basically, the correction is not going to be complete, but it should be a better approximation to xk. So now with this additional information, let's put the multigrid idea into a little bit more mathematical terms.